All right. So I'm aware, welcome back to CS 340. I'm Frank, this is Bayman. Look forward to having a wonderful class with you. I'm aware that we didn't finish the entire slide deck last time, but I looked at the slide deck and I realized actually that all the slides at the very end, we just cover on the second slide in this lecture. So don't freak out about that. Look at the little slides if you want to, so on and so forth. And a suggestion that from the last class, no, don't. So Sean, seriously, you'll see the last slides. We're just going to do the ones that matter here in two slides. And as a suggestion, since the slides are online, you can have them open so that if you have like silly questions, and there are no silly questions, but they're kind of sometimes silly questions. If you have questions about something that I said 2 slides ago, because today, like usual, I'm going to go pretty fast, you can actually flip back and sort of try to figure it out as we're going. And then if you still can't figure it out, then you can ask a question. So today we're going to talk about decision trees. There's still some admin. Don't forget, there's a homework due this Friday. Start. Don't wait, okay? Waiting list people should all get in the class. Grade scope, use the access code that's here. You have to use your ugrad CS email alias as listed here to identify yourself on gradescope.ca. Course web page is here. Go here, go here, go here. The lecture slides, like for instance, those for today are there. Sign up for Piazza. Lots of people are using it. That's good. And the tutorial and office hours have started. Okay, great. Last time we talked about data representation and sort of things that you should do before you start doing data mining or machine learning. The most critical vocabulary that we established last time is what a feature is and what an example or sample is, right? So features are the columns, examples are here, and we're going to eventually, even today, talk about this as the data input matrix X. We talked a little bit about summary statistics and visualizing data. What we did not do is frame a particular problem as a supervised learning problem, okay? So we would have left off if we'd done the last 3 meaningful slides with the following setup, okay? The following setup is, and it's actually true of me, but we talk about this in this course for a few lectures. Let's imagine that you have some sort of horrific food allergy. I actually am allergic to wheat, shellfish, and milk, which is pretty annoying, okay? But anyway, let's imagine that we're trying to figure out what we're allergic to, or rather more to the point, what on a particular day, combination of things that I eat or could eat or whatever, in a sense, what I ate caused me to be sick, okay? So this is some sort of allergic reaction over here. And I'm going to keep a food log that records some quantity, some real valued measurement of the quantity of egg, milk, fish, wheat, shellfish, peanuts that I had over the course of a day, okay? And I'm going to keep a food log, and I'm going to keep track of whether I got sick on that particular day, and I'm going to keep track of what I ate. Okay? And the supervised learning problem that we're going to set up is exactly this. I'm going to want to be able to predict whether I got sick given the food log that I kept for a particular day. Okay? So an input here is an example, a sample, a set of features, right? It's like what the quantity that I ate for in a particular day. That's the quantity of food. And the output is the desired class label, whether or not I or whomever got sick. Okay, and if we build a model of this, then we should be able to predict, right, given a new set of things that's not in this training data, this supervised learning setup here, we should be able to predict whether or not I will get sick or am going to get sick given what I ate during a particular day. Okay, great. So the goal of supervised learning is to use data to find some model that outputs the right label based on the features. Okay, and here the model, which we're going to talk about conditional models mostly, right? The model predicts whether foods will make you sick, even with new combinations. So again, some new day comes along, I eat a bunch of stuff, and I'm like, am I going to get sick or not? I really want to know. If I'm going to get sick, I'm going to take a Benadryl. This is what we want. We want a model to do this, right? And this is really, really important to understand. This is a very, very important point. The supervised learning framework can be applied to any problem where we have input-output examples. Okay? So any problem that you have where you can collect some examples and some output examples, this can be framed as a supervised learning problem. Okay? And lots of stuff can be framed this way. Today, we're going to build towards decision trees, which build towards random forest, which build towards arguably the most immediately profitable method in machine learning. If you want to just go off and like do machine learning, somebody gives you a clean data set, you want to like produce some sort of decent classifier. First thing you should grab is a random forest. Random forest is made of decision trees. Decision trees are made of decision stumps, and we're going to go sort of decision stump, decision tree, random forest, that kind of thing. Okay. But we're going to actually talk about things conceptually in a really nice way, and this framing is super important for you to get and to keep with you throughout your machine learning time. Okay. Decision trees are simple programs consisting of a nested sequence of if-else decisions based on the values of the features. These we're going to call splitting rules, and these programs their return values are class labels. Okay, so an example decision tree based on the allergy example, the food log example that I just gave, is if the quantity of milk that I consumed was greater than 0.5, then just return a classification result, a label, of sick. Okay. Otherwise, if I ate less than that amount of milk, but I ate more than 1 unit of egg, also return sick. Otherwise, return not sick. Okay. Now we can represent this program in a couple of different ways, right? One way is we can represent this as a tree. Okay. And just to make clear, the body of this program over here is kind of missing something to see that as a program, or a method, right? So we could just write def decision tree here, and it takes as an argument milk, egg, shellfish, and has multiple return points. Okay, right? And the goal of supervised learning writ large is actually this kind of program induction. Okay, so I'm going to give you example inputs, and I'm going to give you example outputs. And what I want you to do is tell me what the structure of this program is. Okay, and we're going to do this lots and lots of different ways. We're going to do like deep neural networks, which are called variously differentiable program, like trained by differentiable programming. We're going to do support vector machines. We're going to do linear classifiers. We're going to do decision trees. We're going to do all sorts of stuff. And at the end of the day, really what we're doing is we're going to write meta programs that take data and data in the form of input-output pairs, and produce programs that when you execute them, given an input, will produce an output that's a class or a regression output or something like that. Okay, so a decision tree is just one particular example of this. And again, we're going to build up to this from decision stumps, but we'll see. Here is a particular decision tree. It corresponds to the program on the left, right? So this decision tree is pretty obvious, right? If you consume more than 0.5 units of milk, then you're going to get sick. Otherwise, less than that amount of milk and more egg, you get sick. Otherwise, not sick. Okay, great. So there's a correspondence between this tree form and the program form. You can think of either of them in your head. Let's be clear about one thing, though, is that the variables that we're going to need to learn, we know what the input signature of this function of this program looks like. It is all of the features. We know what the output signature is. It's the domain of the class labels, sick or not sick, 0, 1, -1, 1, whatever. And we know the structure is going to be this combinatorial if then else structure. But what we need to be able to fill in are what is this, and what should we actually return in each of the branches. Okay, the rest of the program structure is going to be fixed, but we need to be able to fill in what are we going to split on, what are the values, and what are the returns for each of the split points in the tree. Okay, that should be relatively straightforward. So I've already said this, supervised learning is really about writing programs given input-output pairs, right? So in this particular case, we're just going to talk about decision trees, and there are many, many possible decision trees. And what we're going to do is we're going to search in this particular case. And in general, when we're doing supervised learning, we're going to do some kind of optimization or search or something like that, that yields a program that is good at our supervised learning problem. Now, what does that mean? It's a little bit of a circular definition, but it means that like our definition of learning or a supervised learning problem is matching the labels given to our input data. Okay, so whatever the definition of learning is, who knows what learning really is, but in supervised learning, certainly it's just building some program that given the training input does a good job of producing the training outputs. Okay. And we'll go a little bit beyond that because it's not necessarily a good thing to exactly produce the training outputs and that sort of thing, but we'll get there. So of this supervised learning procedure, our input is the data and the output is a program. So we're going to map data. So this learner is going to map data to a program. Right? And this specifically is called training. This is a very important word. We're going to use this a lot. This is called training the supervised learning model. And it's different than the usual input-output specification of writing a program, right? So supervised learning in general is useful when you have lots of labeled data, but the problem is too complicated to write a program yourselves, right? It can be very easy. You can sometimes write a program by yourselves. Like if I eat shellfish, I die, right? Like that's pretty easy, right? If shellfish greater than 0, I die. Cool, right? Easy. So please don't mail me shellfish or like put shellfish in like little chocolate bonbons as a thank you present for the course or something like that, because you'll kill me. Okay, so so if the problem is too complicated to write programs yourselves, or a human expert can't actually explain why you assign certain labels, like maybe you have some, like who knows, like very, very complex set of features, and it just so happens that some crazy interaction that nobody can actually describe causes the labels, and nobody actually can do that, or maybe you don't even have a human expert for the problem, right? Maybe there's a new disease and you can't, like COVID, you take an X-ray and you try to say whether or not there's a COVID there. Maybe human experts can or cannot do that yet because they've not actually even seen enough examples to even be able to write down or say even label the data. So like I said, we're going to start with decision stumps, go to decision tree, then go to random forest. So learning a decision stump, we're going to basically do something that's like search and score, okay? Really, we're searching over a combinatorial space, which is NP hard, so we're not actually going to do that. We're going to do something greedy, but the decision stump we can actually solve exactly, okay? So let's do let's go with fitting a decision stump, okay? So what's a decision stump, right? A decision stump is just a really short tree, okay? It's a very simple decision tree with one splitting rule based on thresholding one feature, okay? So again, you can think about this as an if then else statement, right? If feature greater than value return something, R1, R yes, else return R no, okay? So there are 4 things we need to learn. This, and this, okay? Great. And in this tree, you can see there's this, and this. Okay, awesome. So how do we find the best rule, i.e. the feature, threshold, and leaf labels that work for us? So the first thing we have to do is we have to define some sort of a score. If we're gonna like find the best one, we have to say how we measure what's best. And then we have to come up with some sort of an algorithm for searching for the rule with best score. So let's start with a score, okay? So here is like a super obvious score, classification accuracy, right? If we use this rule, I'm going to hand you a rule that looks like this, right? Or like this. If we use this rule, how many examples do we label correctly? So let's just do, this is really obvious, but let's do it anyways. So if we compute the classification accuracy for this rule, egg greater than 1, where we take the mode of each split as the label that we should predict, okay? So when egg is greater than 1, okay, so egg is greater than 1. Let's see, egg is greater than 1, egg is greater than 1, okay? So we should predict 1, right? Great. When egg is less than or equal to 1, we're not sick 3 out of 4 times, so we should predict not sick, okay? Great. So if we predict sick with egg greater than 1, we're good. That's 2 out of 6, right? And if we predict not sick, which is the mode of the alternative, right? We're going to get 3 out of 4 of those right, so we get 5 out of 6 right overall. Okay, so the accuracy of the score of the rule egg greater than 1, where you in each branch predict the mode, is 5 out of 6. Okay, fairly straightforward. Sorry, I have to say that I see some class participants, and it's worth pointing this out, that Yulin has a really amazing icon that is incredibly distracting. I guess that's the lead singer of Queen. Is that right? So great. The score evaluates quality of a rule, and we learn a decision stump by finding the rule with the best score. Great. So let's search for the decision stump maximizing the classification score on this particular data set consisting of features milk, egg, and fish, and with labels sick or not, and we guess we have 6 instances here, right? So let's first choose the baseline rule. This is the last slide. So like, what's the dumbest program that you can write? Okay, you ready? Here we go. This is great. I love it. Okay, baseline rule is define predict classifier. It takes all the features and it returns something, 1 or 0. Let's just say returns 1. Great. In this particular case, it doesn't matter which you return. It could either return 1 or 0. No matter what, the accuracy, it would be 3 out of 6. Yeah. Okay. So that's the simplest decision. It's not even a stump. It hasn't even grown. It's nothing. It's just the tree is a thought, right? So 3 out of 6. If milk is greater than 0, we predict 2/3. Okay, milk greater than 0. Let's look at this. Milk greater than 0. So that's those 3. The mode of that is 2, so that's 2 out of 3 accuracy. Otherwise, we predict on these 1, 2, 3. Otherwise, we predict not sick. That's 2 out of 3 as well. So the overall accuracy is 4 out of 6. And we can keep doing this. Fish greater than 0, predict not sick. Blah blah blah. This gives you a number of accuracies. So let's look at this one. If egg is greater than 0, okay, egg greater than 0. That's these, right? Predict the mode of the labels. 3 out of 3, great. Else predict not sick. Also 3 out of 3 if egg is equal to 0. Okay, so beautiful. We have a lovely decision stump. Okay, and we can keep going. So the high scoring rule here is egg greater than 0 with leaves sick and not sick, predicting the modes as you would. Right? Note that when we search for a decision stump here, right? When we look through this table, we really actually only have to look at the feature, the different feature values, right? So the point is that if we're looking at milk, we really only have to look at milk greater than 0. In fish, we really only have to look at fish greater than 0 or greater than 1.2. And egg, we only need to look at, egg greater than 0, egg greater than 1, right? There's no point in looking at egg greater than 3 because it's not there. There's no point in looking at egg greater than 1.5 because it's the same as egg greater than 1, right? Okay.
Someone's asking, what if you're looking for a combination of features?
This is awesome. Like you can almost, the beautiful thing about this is you can almost predict the questions that are going to come at this at various points. So like everybody now should be thinking about, and this is awesome, Shaunak. This is a good. Oh, was it a question? Who? Yeah. Yeah. Okay.
Yeah, Shaunak.
Great. Okay. So first, we're just looking at a stump. We're not looking at a tree yet. So you can get to combinations of features by chaining these, and we're going to talk about that, right? The second thing is that you could imagine writing a function that's like if fish times egg plus 13 is greater than 42, right? Return something, right? All this does is it changes the combinatorial space that you're searching in, and it makes the search problem harder. Okay. What we'll find is that random forest constructed from decision trees, constructed from chained decision stumps work very well in general, right? And they are constructed by, because they work okay with individual features at each decision point, right? But there are lots and lots of pieces of work where you consider combinations of features. And I pointed out to the last section that, in fact, if you want to look at one of a modern one that does that kind of thing, look at the canonical correlation forest, which is a piece of work that I did with a student of mine at Oxford. And that is exactly the kind of thing that you're after. Okay. We're looking for more levels. Yeah, more levels. Yeah, great. That's true. If we don't add a new feature, will the algorithm catch? Okay, great. I think I got it. All right, cool. Also note that you know, you don't have to test less than, because it's exactly the same. You can either test less than or greater than. It doesn't matter. Just go with one, right? Okay. So we're talking about supervised learning. Let's do a little bit of notation that we're going to use throughout the course. That's one of the nice things about this course design, is that we use the same notation throughout the entire course, and it doesn't get confusing that way. Great. So the matrix on the left, the matrix of which is samples by, or examples or objects by features, is X, and the vector, column vector on the right is the are the labels. That's going to be Y. When we index features, we're going to use D. There are D features, and there are N examples, and there are N labels to go along with each of the examples. So the feature matrix has rows and as examples and columns as features. I'm just going to do that, and it, you know, just think Excel file every single time you do this, right? There's rows that are examples, and then there's features along the columns. The subscript IJ, when we see subscripts, IJ is feature J for example I. This is a pretty standard matrix notation. So that would be the quantity of food J on day I. Xi is the list of all features for example I. So you pick a particular example, and we'll do this in the next slide, but you pick a particular example, I equals 3. Those are the features for example 3. Xj is the column J of the matrix. This is the value of the features J across all examples. So, you know, J equals 4, that's wheat. That would be X superscript J. And the label vector contains the labels of all the examples. So Yi is the label of the example. 1 for 6, 0 for not 6. Sometimes we'll do +1, -1. Sometimes we'll do 1 and 0. Sometimes we'll do you know, more values. We'll do multi-class regression later on. Okay, so don't ask about multi-class regression now. Okay, we've already done this. So x45 is 0.10. X2 is all the values on the second row. X superscript 3 is all of the values in the third column. Okay, and Y equals 4 is the label for the fourth example, or Y subscript 4, I should say. Excuse me, Y equals 4. Y subscript 4 is that. Okay, so in supervised learning, we have a training phase. Okay, this is an important notion, right? Training phase takes the data, which consists of X and Y, the inputs, which is object features, and the outputs, which are the labels, and uses that to construct a model. And this is going to be the program induction thing, and so on and so forth, right? And one example, the only example that we've actually seen so far, is this decision stump, right? So we're going to right now actually write a program that takes the data and produces a decision stump. After you run this training phase, you have a program instantiated. The return is a program. That program can be used to actually make predictions then, right? So you give that resulting program an xi, and you use that model to predict a label y hat I. And this hat is really important, okay? So hat is a common notation in statistics and machine learning for estimate. It's an estimated value of something, right? So our model is going to produce an estimate. It's not going to produce the true yi. It's going to produce an estimated yi. And if we're lucky, y hat I will be close to yi. And in fact, that's the signal that we're going to use throughout for deciding which are good, models. And the training error in this particular instance is the fraction of times that our estimate y hat I of the label does not equal the true yi label, okay? So
I have a question.
yeah, just ask the question. You don't have to like preface it with, you know, we have a question or Frank or anything like that. Just
okay. If fish is bigger than 0, the mode is 1, but isn't 1 also the mode of if fish is 0? Does this mean using the method we would always predict sick using this rule?
Yep. Yep. That may be the case, and we'll see an example of when that happens. Yes.
So the training error is just 1 minus accuracy. Is this always the case?
this is going to be, I don't want you to memorize that, Christopher. Just go with what we've got defined right now, because the training area is going to be different depending on the different models that we talk about, right? And accuracy is going to be just one thing that we talk about. We're going to talk about a lot of different things. So just don't even worry about that right now, okay? Even if algebraically it makes sense. Yeah. Okay. Why not x sub 4 sup 5? Well, we made this choice in this course. Okay, decision stump. Sorry, we got to keep powering on. So decision stump learning pseudo-code. Let's go like write the learning algorithm for a single decision stump. Okay, so the input is a feature matrix X and a label vector Y. Okay. So the first thing you do is compute the error if using the baseline rule, right, which just produces you just predict the mode, right? That's the number of times that the true labels yi do not equal the most common value, the mode, right? Then for each feature j, that's in other words column of our feature matrix X, and for every unique threshold in that column, what you do is you set y yes to the most common label of objects I satisfying the rule. So you basically take the mode of the stuff that satisfies x ij greater than t for all I, right? And you set y no to the most common label of the objects not satisfying this rule. And you set y hat to be our predictions, the actual predictions that you make, i.e. setting everything to y yes when j is greater than the threshold at this point in the loop, and y no alternatively. Right? Then we compute the error. That's the number of objects where y hat I is not equal to yi, right? So cool. Then we store the rule. And this rule, this data structure right here, j is the feature, t is the threshold, right? And then y yes and y no, that fully specifies the decision stump program, right? We needed the feature, we needed the value, and we needed the two return values for each side of the branch, okay? We store it if it has the lowest error so far. We just go through all the columns and all the thresholds, and we compute the, j, t, y, yes, y, no for all of them, and we return the one that has the lowest error. So the output of this program is the best decision stump based on the score, sum score, and that is our model. Okay. Now note this score is going to change in just a little bit. Okay. Great. Cool. Any questions on this? Should be okay. So how much does this algorithm cost? Well, assume we have n examples. We already have that. That's days that we measured. D features, we already have that. That's the number of fruits that we measured. K thresholds. Now, we don't know what K is. That's going to be in the data, whatever that happens to be. That's funny because I turned off all notifications. I have no idea how Slack still notified me. So there's going to be some number of thresholds for each feature. Let's assume that we have the same number of thresholds for all features. We're just going to do an asymptotic analysis here, right? A simple one. So computing the score of one rule, right, costs O(n), right? So we have to go through all the n examples to compute the most common label, the modes for each of the decision rules, right? We need to go through all the n examples again to compute the accuracy, compare y hat I with yi for all I, right? Cool. And in order to actually learn the stump, we actually have to do this k times d times, assuming that there's k thresholds for each of the d features. Okay, so we need to do order n operations, k times d times, which gives us a total computational cost of big O n times d times k to learn the decision stump. Okay, cool. Is that good? That's an interesting question, right? So in some sense, it's pretty cool because the size of the input data is big O n d, right? Like you have n rows and d columns. In order to load that in, right, you have to actually do n times d operations of some kind. So if k is small, you're golden, right? That's about as fast as you can possibly go, right? Unfortunately, if you have lots and lots of individual unique values in all of the features, it could be pretty slow, right? So a fast case is when our features are binary. All the features are just 0, 1, and lots of real world high throughput machine learning algorithms are constructed such that you just make all of your features binary. You just make a crap ton of binary features, and then you can go really, really fast, right? All you have to do is test whether or not the feature is greater than 0, then, right? That's the only threshold. And then the cost of fitting the decision stump is big O n d, so we can fit very, very large data sets, right? If, on the other hand, we have real valued quantities and there's each individual value is unique, then we've got a little bit of a problem because k equals n, and the cost of fitting a decision stump is big O n squared d, and n squared is bad when you have big N, right?
Is this one of the reasons we do feature aggregation?
That's not a bad point, Alan. Yeah, so indeed, right? So feature aggregation means one of, depending on what form of feature aggregation you do, if you actually eliminate features, then D gets smaller. If you quantize features, then K gets smaller, right? So yes, this is one of the reasons why you might choose to do this, because obviously, if you happen to know that you're running a decision tree algorithm, blah, 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 and you have real valued features and you really need this thing to run really fast, then actually quantizing the features will make the thing run quite a lot faster, right? So that's not necessarily true, because if you want, you can look ahead. This is not testable material, not critical for the course, but you should be aware that if you're smart about sorting the features, right, and you do a reasonable job of tracking the right stuff, you can cut down the cost of fitting a decision stump to O in D log n, right, which is a lot better than n squared, right? So you can still fit decision stumps to huge data sets, which is going to be important because we're going to want to fit decision trees to very large data sets. Good questions today, everyone, and nice job, Payman, wrangling them to make sure that the right questions are asked on Piazza versus here. So any questions at this point from the audience? 105, we're at 105, that's great. That's pretty good, actually.
I have a question.
Yeah.
How do you decide the thresholds if you have a lot of decimal values that don't have any clear distinction from when you should cut them off?
Again, it's just unique values. That's it, right?
Okay. Okay, thanks.
Yeah. Wow, a non-payment voice in the class. Thank you, Al. Appreciate it. Cool. Great. Okay. Let's move on. So we've got a decision stump, right? And it's probably, if you're thinking about how we're going to make a decision tree, it's probably starting to be clear, or you're starting to think ahead a little bit like, how do we make a tree out of stumps? Well, it should be pretty straightforward, and it is, right? So decision stumps have only one rule based on one feature, right? This is a super limited class of models. It's usually not very accurate for most tasks. Something like, in my case, right? Again, if if shellfish greater than 0, sick, right? That's a decision stump. It works. It's very, very accurate for me, right? But it's not accurate enough because I'm going to get sick if I have other stuff as well. Right? So decision trees allow sequences of splits based on multiple features, right? So now we're going to have a nested set of if-then-else cases, right? And that means the combinatorial optimization problem is going to be much, much harder, which is why we're just going to not even try to solve the combinatorial optimization problem. We're just going to talk about a greedy algorithm, right? So decision trees are a very general class of models, and they can get very highly accurate, right? However, because of the combinatorial optimization problem, it's computationally infeasible to find the best decision tree. So what we're going to do is we're going to go try to find a decent decision tree that's going to work well in practice, right? So the most common decision tree learning algorithm in practice is greedy recursive splitting, right? And it works well enough in most cases that we don't even have to think about anything else. So what does it mean? It means that when we make the program, we do this if then else thing, right? Else, right? We make a decision about the first thing that we split on, and then we make a decision about what happens in here, right? If blah, 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 so on and so forth. So we split at the beginning, and then we split later, and we split later, and so on and so forth, and we greedily go down and make these splits, okay? The optimal thing would be to fix the tree structure and then combinatorially choose which of the features actually go in these things, right? So we start with full data set, right? So we've got all the features here, and we have the thing that we're trying to predict, which is what I'm going to get sick, okay? So the first thing to know is like, let's run the decision stump algorithm, and let's say that it outputs milk greater than 0.5, and if no, then predict not sick. So let's make sure that makes sense. Milk greater than 0.5, 0.5, no. So these are in red, no, and 3 out of 5 of those are not sick, so we should produce not sick, okay? And let's look at milk greater than 0.5. So 0.7, 0.7, 6, 6, 0.6, 0.6, 6, 6, 0.60. So that's accurate, what, 1, 2, 3, 4, 5, 5 out of 6 times. Okay, so we should predict sick on the right branch. Okay, so that's the output of running our decision stump algorithm on the full data table, right? So we can, now what we realize is that, of course, well, let's not stop here. Let's keep going, right? Maybe we can do better if we don't stop here and we just actually, you know, make two new data sets and run the decision stump algorithm on them and build a tree this way, right? So realize that this thing, right, this little procedure actually splits the data set, right? It makes the red things go down this branch and the stuff not circled in red go down the other branch, right?
Should we keep or discard rows of identical values?
Do we keep or discard rows of identical values? That's a new question I have to think about. That's a very subtle question, and it will be the answer to that is a little bit arbitrary. You can do either. The reality is that you probably want to keep them because the information gain that we're going to talk about is going to affect what goes on there, because you're actually changing the distribution of data items, right? And you'll see what this means in just a second. So we split this into 2 data sets based on the sum. Yeah, go ahead, keep going. Yeah.
Discard and the algorithm should weight it higher.
Well, I mean, now we're getting we're getting fancy. Okay, let's not go there. You can imagine algorithms like this. Yeah.
Do we always choose the best decision stump as the top root of the decision tree?
Okay, Chang-Xi, that's a great and awesome question. So this is I said it really, really fast so I can see how it could go past. We're doing greedy recursive splitting here. Greedy, okay? That means that we're gonna make a choice and we're gonna go with it, right? So we're gonna choose one and we're gonna stick with it. But that is not necessarily the rule that would go at the top if you actually solve the combinatorial optimization problem, okay? So it's greedy, we make a choice and we live with it and we move on. You can imagine doing better, okay? Great. So we split the data into 2 smaller data sets based on the stump, right? And now we have a decision stump, a partial program, right? And 2 data sets. Well, what can we do? It's pretty obvious. Now, we have already written a program that takes a data set, it consumes a data set, and produces a decision stump. So we just actually re-entrantly call the same program, which finds a stump for this particular data set. And here we might split on egg greater than 1, right? Cool. Egg greater than 1 is this row and this row, which is 1. So we should produce sick. Egg, the other is all 0, so that's great, not sick. And lactase rather greater than 0, so milk. Says, yeah, okay, all but this one right here is 6, so it's very highly accurate, right? Cool. Then what you do is you just remove these bad boys, put the new decision stumps on there, and now you have a longer program that's more accurate than the original program, right? Great. So cool. That's pretty much it. It's much more accurate as you add depth. Okay. Any questions about this? We should keep soldiering on. Should be pretty straightforward.
How did we also choose 0.5 for milk?
I understand we're supposed to use, let's see, is there a milk 0.5 anywhere in the data? That's a good question. These detail people. Great, just call it, do we have milk 0? Yeah, we have milk 0. Greater than 0. That's a good question. How many years have we done this? And there's a milk 0.5. Is there no 0.5 in the original data? That's hilarious. doesn't matter. Pretend that the data table is longer and there's a 0.5 in there. It's the same story.
Could we go for some sort of wide partitioning rule instead of splitting into two groups each time?
Yes, and that would be a different kind of force. It would just have a higher branching factor. If we're doing greedy at each level as possible, we choose the best split at that level, not the best for overall prediction. Yes. Cool. And thank you, Chungzi, for the answer for Elias. Great. Cool. So we can try to split the 4 leaves to make a depth 3 decision tree, so on and so forth. We can keep splitting until a couple of criteria are met. The leaves each have 1 label, or we reach some user-defined maximum depth. Who knows, right?
How did you decide how to structure the tree?
We decided at the beginning by saying this is what the structure is going to be. It's just going to be nested if then else's. That is the definition of a decision tree. Okay.
Does the value we choose have to exist in the table?
It does in order for the optimization that we for the computational complexity argument that we made to hold. Okay, we need to keep going.
Do we need to use all the features?
We need to keep going here just a little bit. This course there's good questions, but we just slightly too many. So which score function should a decision tree use, right? Should we just use the accuracy score while we're splitting? Basically, is the question. For leaves, yes, that's very, very, very clear. You should just maximize the accuracy. But for the internal nodes, it's not necessarily true that you should do that, right? So maybe no simple rule, egg greater than 0.5 actually improves accuracy. But that doesn't necessarily mean we should stop. So let me make this point. This is actually a really important point, so pay attention here. So let me give you an example where accuracy as the metric for splitting, like the thing that we're trying to maximize. So like when we're running our little inner decision stump learning rule, we're trying to maximize something. And when we did it, we maximized accuracy. We might actually want to maximize something different as we're doing this. And we're going to talk about the different thing to maximize right now. So if we consider a data set with 2 features and 2 classes, where each data item here corresponds to, X is 1.2 and Y is 2.1. So maybe that's this data item right here, who knows, right? And basically the labels are noughts and crosses, okay? So we can draw the data, the matrix as a scatter plot, and we can put colors and shapes to indicate the class, right? So a decision stump, if we try to fit a decision stump, would divide the space by a horizontal or vertical line. So testing whether or not X1, I1 is greater than some T, so we can pick a T here and pick, or we can make a threshold here and pick either way, right? But the problem is that the mode of the labels for any split in this particular data set is always going to be 0, right? Like the mode is 0. So you have to, it's never going to improve accuracy if we're using this as the thing that we're searching over in our decision stump training algorithm. So the question is, which score function should a decision tree growing algorithm actually use, right? The most common scoring practice is called information gain. And what we do instead of internal nodes is we choose to split that decreases the entropy of the labels the most. And we talked about entropy the other day. Entropy again, and the way we define entropy is an entropy of a set of values, right? Okay, that's weird. But what we said is if we go through the set of values and compute the proportion estimate, the probability of each value in that set, and then we compute the entropy of that empirical distribution, that is something, right? So the entropy of the labels for a split, if we have labels that are 0, 1, we have a certain number of 1s and we have a certain number of 0s, and we can compute the probability of 1 as the number of 1s over the total, and the probability of 0 is the number of 0s over the total, and we can compute the entropy of that conditional distribution, probability of 1, probability of 0, okay? So the entropy of the labels before the split is entropy Y. The information gain is defined as the initial entropy before the split and the entropy of the resulting 2 label sets after splitting. So, and normalized by n yes over n and n no over n as we define those 2, okay? So, n yes is the number of examples, satisfying the rule, right? And the entropy of the labels for the example satisfying the rule, okay? So the information gain for baseline rule, the baseline rule of doing nothing is 0, and the information gain is large if the labels are more predictable, i.e. less random in the next layer, okay? So like if you make one of the resulting entropies or both of the entropies 0, right? then the information gain is the entire entropy of the initial label set, right? That's a good thing, right? So, and the way you make the entropy 0 is you make the resulting subtrees have no label uncertainty at all, right? Okay. So the point of this as being the thing that you should maximize inside the decision stump learning algorithm is that even though it may not increase, you might not be able to increase classification accuracy at one depth, we hope that it would make classification easier the next depth, and it does, right? So here we have this example where accuracy fails because the mode of any horizontal or vertical split would always be 0. But if you choose a split based on information gain, if you, in your decision stump learning algorithm, you maximize information gain rather than accuracy, the split that makes, like this particular split on feature X1 really, makes the labels less random. Everything on the right-hand side has an entropy of 0. So you're gonna have a positive information gain, right? So everything over here, the labels are all the same. So the entropy of this label set is 0. So you have a positive information gain, that's good, right? Making that split didn't improve accuracy at all. Everything is still classified as a 0, but you have positive information gain, right? And in fact, in this particular case, if you keep splitting on information gain, right? So if you keep splitting on information gain, right, where these actually, of course, go all the way across, obviously, and this goes all the way across, but basically you are defining subspaces, you can, just by maximizing information gain, split 3 times and perfectly accurately classify this data set, okay? Where the colors that we show here show the decision boundary in space. So everything that's in blue in this would be classified 0, everything in green would be classified X. And these sort of like decision boundary plots are really, really important. You're going to want to actually understand what's going on with these and think about what's happening here, okay? So we're actually almost on time. Thank you very much for holding back on your questions just a little bit at the end. I appreciate it. So discussion of decision tree learning, right? Decision trees are super easy to implement. They're interpretable. That's really important in modern machine learning, actually. Learning is fast enough anyway, and prediction is blazingly fast, right? So you can also deal with a small number of missing values during training, and they're not that bad, right? So there's some disadvantages, i.e. actually solving for the best decision tree over all possible decision trees is really hard because it's a combinatorial search problem. You can't find the optimal set of rules, but that's okay, because greedy splitting is often accurate enough. Even if it requires very deep trees or is not accurate in some other ways. And we're going to deal with that with random forests. So issues, can you revisit a feature? Yes, obviously you can revisit a feature. That's totally baked into the algorithm. Are more complicated rules possible? Every class, as you did, always starts thinking like, oh, can we do multiple splits? Could we have multiple things? Yes, you can do all those things. But the combinatorial search problem gets much harder. All right, what's the best score to maximize in the decision stump learning algorithm? Who knows? There is no best. It's, you know, we'll talk about that later. But info gain is very popular and works very well, right? What if you get new data? You can consider splitting if there's enough data at the leaves, but occasionally you've got to relearn the whole tree or subtrees. And what depth? That is very application dependent. So, in summary, supervised learning is about using data, input-output pairs, X, Y, to write a program based on those examples. And that program is a program that takes a feature vector and produces a label, okay? Decision trees produce a label using a sequence of simple rules. So the program, the supervised learning artifact, the whatever is a nested if then else statement where you have rules, values, and return values, right? Cool. Decision stumps are basically simple decision trees that are extremely fast to fit in practice. And even though the combinatorial search problem for finding the optimal decision tree is it would be an NP-hard problem to solve, greedy recursive splitting works pretty well, right? And it basically selects a sequence of stumps. It uses a sequence of stumps to fit a tree. You select them greedily. It's super fast and interpretable, but not always the most accurate, although again, we're going to fix that with the random forest. And we talked about information gain, which is what you use to train your random, or your decision stump rather than accuracy at internal nodes of the decision tree training process. So that's it. I'll stay for questions until 5. And next time, let's talk about another of the most important ideas in machine learning. Thank you very much.
All right. Does maximizing accuracy throughout the decision tree potentially lead to overfitting?
Okay, so Fisher, nice to have a question from you. Yes, you're welcome. So we explicitly said that we're not maximizing accuracy throughout the decision tree, right? In fact, maximizing accuracy might lead to the kind of noughts and crosses problem that we talked about, which is that you wouldn't be able to do anything because there's nothing to maximize, right? So we're actually maximizing information gain as we go until we get to the end and we choose to maximize accuracy in the leaves. Yes, and we haven't talked about what overfitting is, but your general idea that a decision tree, particularly a very deep decision tree, is very likely to overfit in the sense that if you classify if you have a large amount of training data and you classify it perfectly, any small deviation from your training examples is likely to put you in a very specific location with a very specific label, right? And that fine-grainedness might not actually be good for generalization. So that's a good point. We'll discuss that later. So one way to deal with that is just to limit the depth of the tree. Dominic, so how do we know how accurate the approximation is? How do we know we haven't gone off the mark completely? So we haven't talked about any of this stuff yet. These are really good questions. In general, we'll use what's called cross-validation for capacity control in this class. There is no real way to know how accurate the approximation is, right? You can, there are generalization bounds that you can look up if you're into like Rademacher complexity and that sort of stuff, but their application to this domain is actually very, very complicated, and they don't give you very good, very actionable results anyway. So the short answer is we don't actually really know how accurate the approximation is, and the proof is in the pudding. So we're all, like I said many, many times, and hopefully this will get into everybody's head relatively soon, is what we're going to care about ultimately is predictive accuracy, right? On some held out test data, right? And that's the thing that we're going to aim to maximize. Which you can't do that directly, and that's complicated. Okay, what's the difference between decision tree and greedy recursive splitting? A decision tree is the output of a decision tree learning algorithm. It's this program that takes feature values, a feature vector, and produces a label. Greedy recursive splitting is an algorithm for assigning values to the subparts of that program, the free variables in that program. What happens when there's contradicting data, same input to different output? Okay, well, you can sort of think about what's going to happen there, right? So there's going to be irreducible error in the tree, even if you were to fit the decision tree all the way down such that that data item lives in its own branch. You would always have two labels there, and there's no way to the maximally accurate thing that you can do in that particular case is just pick one of the values. You're going to get 50% accuracy in that particular leaf. It doesn't really matter. There's nothing you can do, right? Great. Sorry about all the Slack stuff. Got a couple of grant notes. That's really frustrating. Okay. Couldn't we get repeating subtrees at least with our original accuracy idea? You can get repeating subtrees no matter what. That's just true, particularly for deep decision trees. But in general, just to look forward a little bit, we're not actually going to go with deep decision trees because they don't generalize well. So we'll use shallow, but lots of them. And that'll be talked about later. For feature selection, are we going to use some algorithms like forward selection or backward elimination? Oh my goodness, Tianyi. This is like 6 or 7 lectures from now. I'm not sure why we're talking about feature selection right now, but we will generally talk about forward selection in this course, I believe. Because I don't think we should use all the features given as possible. Maybe. Given this question, I'm guessing you have a statistical background, and frequentists would say you should do feature elimination or feature selection. Bayesians would say you use all the features you've got all the time. I live in the latter land in general. Is it possible to have different results from two people using decision tree on the same data? As presented, I mean, as presented, there are a couple of edge cases that we haven't discussed that are going to be fun for you in your homework, right? And those edge cases are what happens when you have multiple rules that have the same information gain, for instance, right? Then you have to choose between those rules, right? And that choice is totally arbitrary. So that's a stochastic choice. It's a free choice, and you can arrive at different trees given the exact same algorithm modulo the random choice that you make when you choose between equivalent rules. Thank you, Gideon. Okay. Any more questions? Possibly use supervised learning to generate a training model for a set of data. Is that too general? What? Is it possible to use supervised learning to generate a training model for a set of data? There's an agreement mismatch there. I don't know what training model for a set of data is. Maybe, Kian, you could specify your question a little bit more. So is the choice of rules based on luck? Gideon, that also doesn't really, no, I'm saying that when you write an algorithm and you have equivalent rules at a particular decision point, you get to make a free choice, right? And the resulting tree, who knows, right? So is the choice of rules based on luck? No, it's not based on luck. You have a free choice. That means that there's going to be variability in the trees, and there will be some distribution of performance given a particular training data set and algorithm. Could you explain the splitting on the previous slide and how it fails accuracy? Let me see if I can actually do this. Whoa, that's not the right way. Here. I assume you're talking about this one. Yeah. So great. Let's pick a point. You pick any point you want. I wish we could be together to do this. I'm going to pick this point. There's more circles on the left than there are X's. You're going to choose circles as the mode. There's more circles on the right. You're going to choose circles as the mode. So this decision stump, if you chose to split on accuracy, would have no way of discerning any of these because the answer on both sides is always circle. Thus, these are equivalent learning rules. You just pick one or none. In fact, you would terminate a learning algorithm because there's no gain anywhere, right? So you couldn't even move. But if you were to make a random algorithm, then you would just, there's no, who knows, right? The variance of the performance would be extremely high because you're just totally picking at random. Okay. I mean, use supervised learning to generate an algorithm better than the greedy recursive splitting one we learned today. What you're talking about, Kian, is actually called meta learning. Yes, you can, but you have to think about the problem that you're actually suggesting a solution to, which is really awesome and super fun to think about, but you have to learn a supervised learning problem for predicting the right move in a tree growing algorithm given a data set. So you have to, given a task. So you have to embed the task somehow and then actually build a policy, basically, sorry, I'm going to use reinforcement learning language, but to make a choice about where to split in that particular problem. That is really hard, but actually is sort of modern research. It's close to automated machine learning. It's also close to meta learning, which are two things that happen in my lab. Great. The accuracy of the baseline rule always 1/2. No, obviously not. If all the labels were 1, the baseline rule would always return 1, and you would have perfect accuracy. Okay, so Vincent, I went to the graph and I hopefully explained it well enough that you can understand. Put the side on the left over here. So you're saying over here is going to create, like, how's that going to increase accuracy? No, that's not going to increase. This is still going to be 0, and these are all going to be, you're going to label 0 on both sides of that. This one, honestly, this is the slide that I, just to be fair to all of you, when I go back and think about this instead of my research and other stuff, every time I look at this, I'm like, the first time I look at it, the side containing X and 0. No, the accuracy doesn't, because okay, yeah, so this side, that would be the right side, not the left side, the other left side. No, because the mode of that is 0. The most, like, 1, 2, 3, 4, I'm not going to count them, but there's more zeros than there are X's, right? And there's no way to divide this such that there's more X's than zeros in any horizontal or vertical split. So yeah, every time I look at this, I have to think, oh yeah, okay, I see. Yeah. But that's the story, right? Okay. Good luck to everyone. I will see you all on Wednesday. Thanks for your time. Thank you, Prima. Love to see you. Yeah. Cheers, guys.